All right, so I'm a little bit far behind on all of my little miniature discussions, and it turns out that technology and I are not getting along well. So we're going to do the rest of this stuff just out on paper so that I have the freedom to make gestures and things with my hands that you guys can't see on MediaSite. I think the first backlog in our discussions were about inductors. So by now we know in Faraday's law, if we have some kind of a, I don't know, maybe a wire or just anything, and we try to change the magnetic flux through it, this thing doesn't like it and it's going to try to fight back, right? By inducing its own kind of induced flux in the opposite direction, because it doesn't like to see a change. There's a lot of ways we can do that, as we discovered and talked about. We can either do it by dB, right, with A and then the dot product, so I guess our cosine, or we can do it with B dA dt and then the cosine, or, you know, we can do BA, I guess this will be like sine. And I think we even got a little bit whimsical and talked about doing a dN dt for the number of turns. These are all great things that we can do in kind of a theoretical case, but realistically, if I have some kind of a device that does induction and it's hooked up to a circuit, then really the only one that makes sense is this. So we want to talk about its self-inductance. If we build a solenoid and we try to suddenly connect it to a battery, maybe with a switch here, boom, we close the switch, we try to put a current in it, and then the inductor says, wait a minute, a sudden change in the current means a sudden change in the magnetic field, and I don't like that, so it's going to fight back. So realistically, when we talk about real inductors, they generate some kind of a backwards EMF of their own, right? So this will be the induced EMF, and it'll be more related to the dB dt part of the flux. All right, so let's take that thought and kind of put it aside. If we wanted to kind of come up with some equation that helps define how much back EMF or how much voltage do we have, we need to have some kind of measure for an inductor's ability to do this. So in Faraday's law, if EMF is, let's say, N d phi dt, we need to ask ourselves questions about how can we possibly change the EMF on our own, or how can we change the flux on our own. So if this guy's in a circuit and it looks like a solenoid, and let's just use the solenoid case, I think we got that. We've got N, the number of turns involved. We'll have B for the solenoid. We'll have the area of the solenoid, and that'll be the cross-sectional area known here, right? So that's A. And then the angle seems not relevant, right? Because everything that comes in is kind of at a right angle. So our next substitution, what's the magnetic field due to a solenoid? I think it's mu naught. It was the turn density, N, and then it's the current in the wire. So if we wanted to, we could also simplify this a little bit and say N mu naught N over L, and I don't like that idea of L, so why don't we call it, I don't know, I'll use a lowercase l in this case for reasons that'll be obvious. And then the current in the solenoid. And it looks like I missed the DDT part here. Whoops. So if we apply this derivative, this is a universal constant. These are just numbers. The only thing that's changing is the rate that the current is building up inside the device. So the voltage looks like N, I got mu naught N over L di dt. And I guess all of this stuff in front is just some constant. So let's define that constant as L, and we'll call it the inductance of the device. So this can be defined as, I guess, L times the change in the rate of current in the device. So this is just one way of defining the value of the inductance. It's just the formula. V on the inductor is L dIdt, where this is all those constants that we would have done in Faraday's law when we combine all of this stuff together in that case. And it looks like, gosh, I am really dropping the ball here. I'm missing the area, the area, the area. Yeah. So I don't know, maybe in the book, you've got some L for a solenoid, and maybe it's defined as something like mu naught, I guess, n squared over length times the area, and maybe it's pi r squared, or maybe, I don't know what it is. It's whatever. If you guys have this formula and you're just using it, at least now you know this is where it came from. Okay, another way that we can define the inductance, that's just one value of it. When we pull out an inductor and just look at it, we have to say, well, this needs to have some number that's never changing, right? It needs to be a value that's inherent to the device. And this whole issue of having some amount of current in it is nonsense. I mean, it's craziness for us to deal with. So we want to divide out everything about this formula for Faraday's law, somewhere up here. We could just divide out the current part. So another definition of the inductance is to look at the total amount of flux, and we'll just divide out the current. And if we try it out in this situation, and remember, this flux will contain a magnetic field that's current dependent. We want to just divide out the current because it's a variable, and we want to get rid of all variables that are non-constant. So in this case, we have NB A over I, which is N, mu naught N over L, I, A, and we'll divide out the I, and what do you know? It's the same formula. So here are two definitions for ways that we can think about the flux. It either comes from directly doing Faraday's law, or it can come from just kind of simplifying out all of the non-variables from this stuff in the flux. All right, so some considerations, at least in a circuit as far as it's concerned. My students will remember that we have different kinds of components that we have experience with. Let's say this one's the battery. We know the capacitor looks like that because it's parallel plates. We know in the United States the resistance looks like that, but I always write it the European standard, like that. And now we have a new device, and it's called the inductor. Generally, it's made of solenoids, so it kind of makes sense to describe it as a coil. And because these two symbols look a lot alike, especially with my bad handwriting, they both pretty much just look like that. So that's the reason that I have a tendency of choosing this version. But here we have it. It's just a coil. Let's ask ourselves what the inductor would do in some kind of a circuit. So let's draw a circuit that looks like this with a switch. And let's say I've got some kind of an inductor here. And at time equals 0, I close the switch. What do we expect to happen for the current? Well, at I equals 0, or at time equals 0, we close the switch. What does the inductor want to do? It sees no magnetic flux through itself. It doesn't want to see any change in magnetic flux in itself, so it's going to resist and fight this battery and try to set the current to be 0. Okay, so in a way we can say that the inductor turns itself into a brake. So our circuit would be replaced here with a broken wire at this extreme when time is equal to 0. But you know it can't win forever, right? It needs a changing current in it to really maintain this voltage, and eventually the inductor is going to lose its battle against this battery. So at a long time later, let's say time is infinity, the current will be just I max. And that means that the inductor will turn itself into just a short circuit or a wire. These two cases are the easiest. At these two extremes, no problem. But what's going on in the interim, between those two extremes, it's a little bit more complicated. So let's say this is the current, and I'll keep lowercase for consistency. I know here it's 0, and here, let's say this is Imax. And this can be determined by, resistances in the circuit, right? The inductor might have an internal one, or maybe we've got just an RL circuit right here. So I know that this has to be true at 0, and this has to be true a long time later. And by experiment, we get a curve that looks a little bit like this. And that looks like an exponential growth or decay curve. And we have some experience with these, right? I is two options. It's Imax, e to the negative t over some kind of time constant, or it's 1 minus e to the negative t over some time constant. And we've done exactly these things with capacitors in RC circuits. So of our options, you just take a guess and double check both compared to what we expect to see up here. At time equals 0, I'll plug in a 0 and try to find zeros like that one. So if time equals 0, e to the 0 is 1, Imax times 1 is Imax, and we're saying the current is maximum at time equals 0. And does that make sense here? No. Just for clarity, or I don't know, completeness, 0, e to the 0 is 1, 1 minus 1 is 0, I equals 0. That's our correct formula for the, I don't want to call it charging, so let's say it's either warming up, or let's say maybe the energizing inductor. Likewise, if we made this circuit maybe a little bit different and now said, let's say that instead we made the circuit look like maybe this, where I've got a battery, I've got, let's say, an inductor. Let's put a resistor over here this time and make this look a little bit more like that one lab that we did. Here's our switch in position, nope. Ah. Yeah, let's make this our switch. So when I connect it this way, I've got the inductor just doing its thing, right? And it's doing the charging up equation we did before. And if I suddenly close it and turn it to B, what did we have right before the switch closed? I had a current here in the inductor. So now we're switched over here and closed. At time equals 0 in this case, the inductor doesn't want to see any change in the current. So it wants to maintain and keep the current flowing. Whatever it was doing right beforehand, it's trying to make it stay. Okay, and then a long time later, then this will trend towards 0 as the inductor runs out of energy to keep pushing that current along in the circuit. So here you go with the two versions of the equation we had last time, right? It's one of these two, so we'll go back and just ask yourself, which one makes sense in this context? Is the inductor trying to fight it, or is it trying to stay on? Right? And then just ask yourself which makes sense, try it out at the extremes, and you've got your formula set. Okay, what should we talk about now for the inductor? We should know some things about the time constant, I guess. In the RC case, where this was a capacitor instead, let's look at the current versus whatever formula. And let's make it the same circuit at the moment we turn it to position B. Now we'll turn it to A. At A, I've got this circuit just turned on, and this is either a capacitor or an inductor, so let's just call it a mystery box, right? It's one of these two components, either L or C. In the C case, what do we notice immediately? Right when you throw the switch, the capacitor wants to take charge as fast as it can. We're going to see a maximum amount of current right away. And then as the capacitor fills, it chokes off the delivery because it can't take anymore. So why would we keep delivering? If it was an inductor, right at time equals 0, it wants no current, and it takes a while for it to build up and finally get there. Okay, so these two are kind of the opposite equations, right? Capacitors and inductors are kind of, in a way, evil twins of each other, right? They have very similar behavior, but completely the opposite behavior of one another. When it comes to finding what is the time constant, the RC time constant, we remember, was just R times C. And I think we remember the units for that were ohms times a farad. And an ohm is a volt per amp. A farad is a coulomb per volt. That's a coulomb over a coulomb per second. That gives us a time constant just in terms of seconds. Okay, the RL time constant is a little bit different. Its definition is what? I think it was... I think it's L over R. And we can check that because the units of this are a Henry over an ohm. And I know the units of a Henry are really ohm seconds. So these guys cancel, and I've got seconds. So this is kind of an interesting parallel, right? The component is on the top in both of these formulas, but the position of the resistor is on opposite sides. And that's just another weird artifact, right? That shows kind of an anti-complementarity between these variables. So numerator versus denominator, dropping versus climbing. They're very similar, but they're also very opposite. All right. So actually, I think that covers most of what you need for just the inductors by themselves. We know how to make them from scratch. We know kind of what their behavior is in a circuit. And we also have figured out some of the unit issues for the RL type circuit. So I think we're pretty much good on just the inductors.